Additive manufacturing is an interesting system to secure. Like many cyber-physical systems, the data and processes of AM go through transformations from a digital file to a physical result. Unlike a lot of those other systems, which could be running power plants or whole factories, data in AM is portable, reusable, stealable. What I'm presenting today from our paper, Encryption is Futile, is a novel approach to stealing that data in a way that completely circumvents digital protections like encryption. First, though, we have to cover some important background. Additive manufacturing is a family of manufacturing technologies that build up objects by selectively applying and fusing together layers of source material. It's been going through a growth spurt in the last few decades, moving from early applications in rapid prototyping to producing end-use functional parts in plastics, metals, and more exotic materials. The features that have fueled this adoption, its flexibility and deep computerization, also expose it to unique security threats. AM provides a few advantages at the design level. Manufacturers like GE have taken advantage of producing complex internal geometries in one production process to consolidate their parts, like with the LEAP jet fuel nozzle. But GE is an enormous company with enormous design expertise. How can smaller companies take advantage? The market, so far, has responded with outsourcing. Contract additive manufacturing has flourished in recent years, with dedicated firms offering AM as a service. These companies accept designs from their customers, work with them to produce a manufacturable version, then make an agreed-upon production run. But what if your manufacturer is malicious? A malicious contract manufacturer represents a man-at-the-end threat model, which is notoriously difficult to defend against. Solutions have been proposed in the AM security literature for crypto-heavy, trusted platform module-backed approaches. Some of these have even made it to market. Identify 3D, one such company, has partnered with EOS, a major printer manufacturer, to integrate their system into new EOS printers. I'm going to show you a way around all that encryption, one built into the design principles of 3D printers. This is our test printer, the Lulzbot TAS-6. It's a fused deposition modeling printer, which forces plastic filament through a heated nozzle. The filament fuses to itself and hardens as it cools. The shape is produced by moving the printhead and bed relative to each other. This model uses a Cartesian coordinate system, meaning the position is actuated by stepper motors controlling linear X, Y, and Z axes. Bipolar stepper motors are simple. 2 phases of current and a gear-like internal rotor. The movements this rotor allows are what give the motor its name. Instead of a smooth and continuous motion, the motor can step positions, ratcheting forward a fixed amount of rotation without any feedback control. Now, the stepper motor is a direct current motor, but for torque control reasons beyond our concern, they are typically driven by a sinusoidal current, which looks about like this. Each maxima and minima of the waves cause the motor to move forwards or backwards 1 step. This is the foundation of our approach. The current is in direct control of the stepper motors, and the motors are in control of the final object's shape. No matter what security measures you apply to the data, it must eventually be decrypted and used to generate control signals for the motors. A man-at-the-end attacker can intercept those control signals. This traces from our Lulzbot, captured using an oscilloscope with inductive current clamps on the motor wires. The rest of our approach proceeds from here, using captured current data to reconstruct the shape of the printed object. The programming we did to implement the approach is extensive, and the published version of the paper goes into detail with description and pseudocode. Here in the presentation, we'll restrict ourselves to the highlights. First, we need that data. We capture both phases of the stepper motors controlling the X, Y, and Z axes, as well as the motor controlling the extrusion. The captures have to be synchronized and run for the duration of the print. If we visualize that captured data, it produces our trace here. Now, there are only 2 phases per motor, but 4 sine waves in this output. We duplicate and invert the 2 traces to simplify processing them later on. This trace is taken during continuous, unidirectional motor movement at a fixed speed. Looking only at the peaks of each wave, you can see that they come in a fixed, repeating order. This is the most basic pattern we have to recognize, but it's not the only one. There are 3 other behaviors that make up a full trace: startups, dwells, and reversals. This is what the current looks like when the motor begins moving from a dead stop. Note that the phases are not peaking at the same level. They have different DC offsets, which converge to an offset of 0 over time. This complicates automated recognition of the peaks. We have to detect them relative to the prior and following current values. Something similar happens when the motors come to a full stop. The current reaches its peak and then gradually trails off, approaching 0. When it starts back up, we see 1 or more peaks worth of unequal DC offsets once again. This happens when the motor is reversing direction. The firing order of the phases changes, and the pattern of peaks is reversed. Detecting this allows us to track motor direction throughout the print. In our implementation, we recognize all of these trace features by constructing a time-stamped list of peaks and searching it for changes in firing order and periods of inactivity. In a real trace, though, that presents a problem. So far, these have been clean, isolated trace features. Unfortunately, most of the trace looks like this. This is a mess. The motor is doing 2 reversals in succession with a single step in between. The sinusoids are badly stretched and the peaks are indistinct. The motor doesn't care, of course. This wave produces the correct motions. We just have a harder time recognizing them. Handling the error cases generated by these bad sections made up a lot of the technical challenge of the paper, and is also what we're going to mostly skip. Suffice it to say that we can recognize sections that are malformed and attempt to put them back into shape. After generating the peak list, things get much easier. At this level of abstraction, the printer's behavior can be modeled with a simple state machine, which takes in the peaks and spits out a set of points where the printer extruded filament. Run a few models through it, do some visualization, and the simpler models we tested are visually flawless. As we get into the medium complexity models, there are some visible errors, but still a high level of accuracy on more complex models than previous reconstruction approaches. The largest and most complex models remain recognizable but are clearly experiencing positional drift. We tested our reconstruction approach against a set of 10 models ranging from a 14-minute cube that produces an 80,000 large point cloud up to the Stanford Lucy model, which prints in 4 hours and generates a 2.5 million large point cloud. Quantifying the error is challenging, which we'll talk about, but we chose to report it in terms of bad sections. Whenever an invalid order of peaks is found, we know that there was a mistake in our reconstruction. Our approach attempts to correct it, but the error rates we report are as if every point in the bad section was wrong. By those standards, we had an average error rate of 0.79% across all 10 models. The difference between that statistical result and a look at the output of the more complex models is revealing, to say the least. This reconstruction of the Stanford Bunny model generated just 1% error, and yet you can see the reconstructed model is completely unprintable. The cumulative effect of those errors across millions of points is drift. Properly evaluating print reconstructions is going to require a metric that accounts for both spatial similarities and printability. Here I give a tip of the hat to Gao et al., whose use of the Hausdorff distance for their own comparison is a step in the right direction. A closer comparison of the reconstructed model to the printed object reveals that the printing process involves some distortion of its own. The original model is processed by a slicer before it can be printed, and the slicer makes a few modifications. One of these is to place the printing toolpath slightly inside of the object's outer perimeter. This makes sense. The filament has a diameter and changes shape as it cools. As a result, a reconstruction from the printer movements alone is going to be smaller than the original by that same offset. There are multiple other slicer settings that handle physical deformation of the print, which would have to be accounted for to achieve a more accurate reconstruction. So, what to do? I would hate to introduce an attack and offer no defensive suggestions. Technical solutions for this kind of attack do not currently exist, and I suspect that anybody waiting for them will be waiting for quite a while. Our suggestion then relies more on policy. Risks that can't be removed have to be mitigated, in this case by not outsourcing sensitive designs or anything where counterfeiting would be a major issue. Frameworks like the National Institute of Standards and Technology's cybersecurity framework can help with assessment and analysis. Now I'm going to address a couple of questions in advance. First, can you encrypt a signal to the motor? No, not really. Small caveat, you could, instead of that, design your AM system so that it uses actuators that generate control signals with an embedded controller and keep the analog version of those signals very close to their endpoint. Such motors do exist, though they are expensive, and if anyone is crazy enough to build their AM system around them, I would very much like to get my hands on it. Generally, though, if your printer is subject to man-at-the-end attacks, the attackers will gain access to the signals. All you can really do is inconvenience them. Why didn't you use machine learning? Well, because I thought it was unnecessary and uninformative. A lot of other approaches to reconstruction in AM security have relied on some form of machine learning on a side-channel dataset like ours. Some of them have achieved notable success. But machine learning is normally applied when you think you have no chance of a deterministic solution. It and other stochastic approaches, things that use statistical analysis to find their way to a good enough solution, are best applied to problems that are just hard, in the complexity class sense of the word. I did it this way not only to improve the results, which I feel we have, but to show that this is just a solvable problem. It's based on well-understood engineering principles inside of a mostly deterministic system. So yes, you could turn a neural network loose on 400,000 sample runs and generate a statistically significant solution, but why bother? You can just solve it. So, final statements. We've demonstrated a novel man-at-the-end attack against additive manufacturing for stealing model geometry. It's advanced the level of side-channel reconstruction in the field, but also revealed the weaknesses of metrics in the area, pointing at future work not just improving the quality of our reconstruction, but the meaningfulness of the tools we use to measure reconstruction. Hopefully, it demonstrates to concerned parties that you cannot secure an outsourced manufacturing process, no matter how much encryption you apply. Thank you for your time, and if there are any questions, I'll try to address them now.